This is a short video on constant pressure calorimetry. I'm going to carry out two problems, but I want to give you a little bit of background information as well as how it's done in actuality. This is something that you haven't learned in the past. All right, so maybe I'm going to throw in a third problem here. So how calorimetry really is done in like the real world is this: you have a device called a bomb calorimeter, and what you have is a chamber here which basically absorbs, which is basically the system. All right, and heat can be, and because the chamber can't change in volume, any transfer energy is in the form of heat. So either heat can leave and go into the water surrounding the system, or heat from the water can enter the system. And in either case, what we can do is we can measure the delta T using a thermometer. Now, the reality is that we don't use MC delta T usually for these devices, because what they do is they basically carry out a series of chemical reactions which they know how much energy is absorbed and released during the process. At some point, they determine what's called the heat capacity of the device. So that's a big C as opposed to the little c, and that's just basically going to be joules per degree Celsius. Notice there's no mention of mass here, because why remeasure the mass of the water if it's the same mass of the water every time? And what they'll know is how much if it changes by a certain number of degrees, they'll know specifically how much energy was absorbed or released into the water. Okay, or absorbed by the water or released from, lost by the water into the system, and so we measure it that way. Just be aware of that. You'll note the absence of the grams there. Okay, and if you do that, you basically, if you're given delta T, you can immediately figure out what the value of Q is. So if you have, like, you can do this other formula, which is basically Q equals big C times delta T. So sometimes you'll see that being used somewhere. Be aware of it. Okay, that's not specific heat capacity, it's just called heat capacity. Okay, so let's get back to like some of the stuff that's probably more likely, just old style review things. So imagine you have 2.7 kilojoules of heat being added to 150 grams of water at 12 degrees. What will be the final temperature? All right, so since you're dealing with a change in temperature, for those who don't know, you're going to use this formula. This formula is for melting and freezing. This is for boiling and condensation. Okay, and there'll be cases where that's used. All right, and you'll see that in some of the worksheets that you get. Okay, so I've got enough information here, and the one thing, I'm picking this problem because it's the one some students stumble over, because they're being given an initial temperature, and basically the best or easiest way I think to always solve this problem is basically to solve for delta T and know what's going to happen to the change in temperature, which should be intuitive, I think, to almost anybody. So the first thing you do is you take, this is our Q right here, this is our M. We know the C for water is 4.18 joules per gram per degree Celsius. Obviously, this would have to be given to you. So the one thing that's really important is this is in joules. This has to be in joules. So you have to know this is 2,700 joules. It's equal to the mass, which is 150.0 grams, times 4.18 joules per gram per degree Celsius, times your delta T, which is basically your X value, and then essentially you solve for everything, which means I'm going to pause and go get a calculator. So when you do the math here, you get delta T is equal to 4.3, let's say 1 degrees Celsius. And since you're adding heat, you know the temperature of the water is going to go up, so you basically go, 12 plus 4.31, and that gives you 16.31 degrees Celsius. I'm not really doing a good job at sig figs here, but that's basically how you use that formula. Now, sometimes they give you heat loss, heat gain problems, which is something like this one on the next page. So you have 15 grams of aluminum, specific heat 0.90 joules per gram per degree Celsius. I wrote that. I'm pretty sure that's the number, but I might be wrong. I don't think it matters in terms of understanding how to do the calculation. And the piece of aluminum is at 95 degrees Celsius. It's dropped into 30 grams of water, which is at 14 degrees Celsius. And they ask you what the final temperature of the water is. Now, the assumption of these types of questions is that the heat that's lost by the object at the higher temperature, which is clearly the aluminum, right, is going to be equal to the heat that's gained by the water, which is at the lower temperature. Okay, if that's not the case, then you really can't solve this problem, which means essentially you've got MC delta T equals MC delta T. Now, this is the toughest type of problem because it's algebraically annoying. That's the best way I would describe it. So you really have you have 15.0 grams of aluminum times the specific heat, which is 0.90 joules per gram per degree Celsius, times delta T. I tend to like to set it up this way, where I like having positive values. So basically, I would do something like this. I'll go, so it starts at 95 minus X, X being the final temperature. But on the other side, because since X is a lower value than 95, it gives me a positive number. Otherwise, I end up with negatives that fly around. You can do it. I had a student last year who was really great and insisted that, should do it a different way, but I preferred this. So, and on the other side, I would have the water with the 30 grams times a 4.18 joules per gram per degree Celsius. But I would do, for that one, do X minus 14. And now I've got to do a whole bunch of algebraic distributing, and this is why, it's not like a fun job to do this type of problem here. So I'm going to pause and distribute, and then I will combine like terms. Fun. Alright, so what I did was I distributed everything. So 15 times 0.90 times 95, it gives you this number here, 4275. And, I'm sorry. Uh-oh, teacher made a mistake. Stop. Never mind, teacher didn't make a mistake. Okay, so 15 times 0.90 times 95 is 4275. 15 times 0.90 is 13.5, etc. and distributed here as well. And then what I did was I moved the negative stuff over, basically. So plus 13.5x over here, plus 17, and so this goes bye-bye, and this goes bye-bye over here, right? And so I get this thing right here, and then I basically solve for x, and I get x equals 43.4, and that is the degrees Celsius. I didn't do units because I was running out of space here, and also I was running out of time. I wanted to keep it short. The main point is you can get the final temperature. There's lots of these different formulas that involve heat loss being equal to heat gained. Just really be very careful about substitutions and distributing. You should be able to get through them. They're not actually difficult. They're just painstaking and a bit annoying.